So we have Doron Ravid and Elliot Lipnowski talking about credibility, strategic communication, and information design. Doron led the first part of the tutorial, and now Elliot is about to start the second part. So thank you again both for doing this, and I guess we'll run until 1.
Okay, wonderful. So thank you, Laura and Manolis, for your organizational work and having us here, and thank you everybody for sticking around, and thank you, Doron, for setting the bar unattainably high for me. So let me get started. So what we did, to recap, in Doron's part of the tutorial, was we looked at these kind of these two polar opposite cases. So first, thinking about communication games, we looked at the full commitment case, where sort of we just assume that the sender's credibility is guaranteed and ask what information they would want to provide. So that's the Bayesian persuasion model. And we looked at the no commitment case, which we think of as the extreme case of no commitment being cheap talk, where I can just send whatever message I want, a la Crawford Sobel. And we looked at our recent work on this case that made the substantive and simplifying assumption that the sender has transparent motives, that the sender's preferences are state independent, and saw how the same belief-based approach that was fruitful in studying the case with full commitment is similarly fruitful in studying under this assumption on the environment, is particularly a fruitful language, a fruitful and tractable approach for thinking about this no commitment case. So what I want to do in this part of the tutorial is I want to look at the middle ground and think about models of communication with partial forms of commitment. And so now this is going to be there's a big literature here, or many literatures, and sort of so I'm going to be selective in what I talk about, and one organizing principle that we've used to select what to tell you about is we're going to focus on models that are amenable to this same belief-based approach, right? So in a little more detail, my plan is to do, so I have the talk, loosely chopped into two. So one is I'm going to look at a model that we ourselves have studied, which is a particular parametric model of partial commitment that's going to enable us to talk about the degree of commitment power that the sender has. And the form it takes is that that commitment power is stochastic, and with its probability being a useful parameter. And we're going to make the same tractability assumption as I was talking about before, which for similar reasons we think is also an interpretable substantive assumption, that the sender has state independent preferences, and this is going to enable a useful belief-based approach for us. And then after going over that model, I want to talk about other more qualitative notions of partial commitments, different ways in which you can have a mix of being able to commit and not being able to commit in a model of communication. And so, I'm going to talk I'm going to say a small to medium amount about each of these three cases. So manipulable correlation, where basically I want communication to be robust to the sender being able to manipulate the correlation between the state and the message they send. Mediated communication, where I'm going to allow the sender to have access to a trusted third party, but still require the sender to, you know, satisfy relevant incentive constraints in interacting with that mediator, with that third party. And long cheap talk, which, you know, extends the cheap talk model by allowing richer but still fully decentralized communication. And then I'm going to touch like very, very briefly and on, you know, on some other qualitative notions of partial commitment. Okay. So, so the first thing I want to talk about is this model of stochastic commitment. So this is a model that I'm going to tell you about that has appeared, that's kind of introduced in 3 different papers. And the one whose results that I'm going to actually be telling you about is the one that we've written, which specializes to the case of state independent preferences. And so the basic idea is we're going to look at a model in which the sender can commit with some probability. And that probability, we can think, which is just a parameter of the model, we can think of it as capturing the degree of credibility. Okay, so here's the model in a picture. Okay, so I'm gonna, wherever I can, I'm gonna use like recycle notation from the first half of the tutorial. So there's a state theta, and having seen the state here, let me write things in order. But this is so the picture is just a schematic, you know, way of thinking about what the model is. So the sender is first going to publicly announce a Blackwell experiment. So this is like an official reporting rule. So it's a map that takes the state into some distribution over messages. Then the sender is going to privately observe the state after having committed to this official report. And then the realized report M, the realized message that the receiver gets, is going to come from one of 2 sources. Okay, and the probability of that is a parameter of the model. So with probability chi, which is a mnemonic for credibility, with probability chi, the report is going to be drawn mechanically from this official reporting rule. Okay, but with complementary probability, this choice does not bind the sender, and the sender can just choose to send whatever message they choose to send. All right. Now the receiver sees the message, but doesn't know which of these 2 events has transpired. So they don't know whether the message is coming from a freely choosing sender, or whether it's generated by the official report. So they see this message and then they choose an action. And again, we're going to assume that the sender has state independent preferences. Okay. So let me just first point out that the kind of the extreme cases are cases that we already understand. All right. So if chi is equal to 1, so then this step, what this reads is that the report is drawn according to the official reporting rule. It's drawn according to the experiment that the sender chose up front. And so we're looking at exactly the Bayesian persuasion game. Okay, now if chi is equal to 0, then what this says is that the sender who has seen the state chooses what message to send. And so now the game when chi is equal to 0 is not literally the cheap talk game. The game when chi is equal to 0 is the cheap talk game augmented by an initial stage where the uninformed sender makes this publicly observed choice that doesn't affect anything in the future. Okay, so it's sort of it's cheap talk with an irrelevant preamble. So as far as anything we're going to care about for outcomes of the game, this chi=0 is the cheap talk model. And because we're assuming S has state independent preferences, this means that when chi is equal to 0, we have all of the results of the cheap talk model that Doron was telling you about in the first lecture. And when chi is equal to 1, we're just looking exactly at Bayesian persuasion. Right? Okay. So what we're gonna do is we're gonna talk in this model, and so by the way, I should just say I'm this is the model that I'm gonna go into the greatest depth on. But even this I'm gonna do it, substantially in substantially less detail than what Doron was doing. Just to give kind of an overview of how the model works. Okay, so what we're going to do is we're particularly interested in this model in understanding the sender optimal equilibria and the sender optimal equilibrium payoff toward thinking about how chi affects it. So how the degree of credibility affects communications outcomes. Okay, so now in order to answer this, we're going to give you a geometric characterization, which is somehow analogous to the concave and quasi-concave envelope results that you've already seen, and this characterization, as should not be shocking given that the model generalizes both Bayesian persuasion and cheap talk, the characterization is going to incorporate elements of the quasi-concave envelope and of the concave envelope. Okay, so at a high level, the way we should think about this characterization is we're going to end up using the quasi-concave envelope to understand payoffs associated with messages that S sends when they have the opportunity to influence. And we're going to use concavification to understand the value that can be extracted from messages that are only in equilibrium sent by the official report. Okay. Now this is going to turn out to be sort of the value that we extract from kind of these two different events turns out to be non-separable. And the high level reason why is that I have incentive constraints that go across these two events, in that if an official message, so if a message that is meant to be sent by the official report is too tempting to the sender, then the sender, when influencing, will want to send that message from the official report. And so what we're going to the way the relevant program is going to deal with that problem is to cap the value that the official messages are allowed to give to the sender, and then concavify this capped value function. Okay, so let me build up to the program, which I'm I'm not going to give you a proof or even much of a proof sketch of this characterization of the optimal value, but I want to build up to its precise statement. Okay, so first we have our value function v, which is exactly the one that we were playing with in the previous lecture. So let me just let v bar again denote its quasi-concave envelope. Okay, so we would know v bar of mu naught is if we were in a cheap talk world. So if chi were equal to 0, this would be our optimal value. Okay, so we're going to define this. Okay, so now, given a hypothetical belief gamma, I want to define this other funny function. Okay, so what is this something just, sorry, okay, came back. That was odd. Okay. So right. So given this other, so given some hypothetical value gamma, I want to define a function where I take the value function, but I cap it at v bar of gamma. Okay. So I'm going to show all of this construction in a second. But hopefully this is at least mathematically clear. And then I'm going to define the same thing with a hat to just be the concave envelope of it. All right. So let me give you the program the program whose solution gives us the optimal value of our sender in this model of partial commitment. Okay. So I'm going to think of splitting the prior into two events, or like into two different beliefs. Okay, so my two beliefs are going to be beta and gamma. So what these are going to be in the relevant equilibrium that we back out of this construction is, so there are messages that an influencing sender would willingly send. Okay, so there are messages that the sender, if we are in the 1 minus chi event, like messages that, are profitable enough to send, that they would be happy to send them. Okay, so let gamma be what would be a hypothetical, let's say a hypothetical observer's belief about the state if all they learned was that one of these, good messages was sent. Okay. And let kappa, or sorry, let k be the probability that such an event that no such message was sent, and let beta be the belief I would have from the complementary event. So beta is the belief that I would have about the state if I learn if I see that the sender sent a message that must have come from the official report. Okay. So I'm going to choose these. So in this program, we're going to choose all three of these objects. Okay, and the payoff that we're going to get is so from this event that a good message was sent, we're going to get, so what our cheap talk model, or what our analysis of the cheap talk model tells us is that this quantity, this v bar of gamma, is the highest possible payoff that I could get from equalizing the sender's payoff across all of these messages. Okay. And then so the value that we're going to be able to extract from all of the other messages is, so we take the value function and we say anytime a payoff is higher than this v bar of gamma, which is going to be the payoff that the influencing sender is going to get in an equilibrium, we're just going to replace it with the minimum of the value function and this v bar of gamma. Okay, so we're just going to mechanically force the payoff to not be too high. But then other than doing that message by message, so what this concavification is going to reflect is that we can still choose exactly what information the official report gives when sending one of these bad messages. We can flexibly choose what information it gives to maximize the expected this like to maximize the expected payoff, subject to, you know, like when I arbitrarily, or sorry, when I mechanically force all payoffs that it's giving from any message to be below this cap. All right. Now the constraints that I have on these objects are, so one is just a Bayes plausibility style constraint that says my expected pay, you know, my like my belief about the state given one event, the appropriate weighted average of that, and my belief about the state given the complementary event, that has to be equal to my belief about the state ex ante. And then the other constraint, which captures, you know, which captures credibility, is, so I told you that these this gamma is supposed to capture or this gamma and this 1 minus k are meant to capture the event that the sender is sending one of their best possible messages. Okay, one of their messages that's going to give them the highest possible payoff that they can attain in this equilibrium. Well, it has to be that under their under their own incentive compatibility, it has to be that that any time they are freely choosing the message, they send one of these good messages. And so it has to be that. So for any given theta, 1 minus chi times mu naught of theta, that's the probability. That's the probability that the sender can freely choose the message and the state is theta. So that has to be at least, so anytime that's true, it has to be that also the state is theta, and the sender is choosing one of their preferred messages. And so, you know, containment of these events gives me a ranking of these probabilities. Oh, sorry. Okay, so let me sort of describe how you can read off of this. And so, right, so so our characterization is that this is the like this program that I've given you, which we can compute just from, you know, this value, which can be computed from combining the types of computations that you know, go into the concave and quasi-concave envelope formulas, characterizes the sender's optimal value. Okay, so let me, you know, describe, you know, like just show in a picture how we can you know, how we can actually compute the value from a given beta, gamma, and k. Okay, so first, say I have my value function here in black, my v is in black, so we can draw its quasi-concave envelope. So that's, you know, here I just fill in, in red here. So I sort of interpolate this gap. And so now I have a drawing of my quasi-concave envelope. So say I have a gamma here, and I want to compute the capped quasi-concave envelope. Okay, so sorry, what I just said. I want to compute this capped value function. So what I'm going to do is I'm going to take the black curve and I'm going to replace it with this orange curve here, and then go back to the black. Okay, so this is my capped value function. And if I wanted to, so here drawn in orange together with the black down here. And so if I want to concavify it, I'm just going to, so what this will be in this particular example is I just interpolate from here to here, and I interpolate from here to here. Okay, so here's my whole concavified capped value function. And so if you give me a gamma, like a gamma that's here and a beta that's here, and you choose your k so that this thing satisfies the Bayes plausibility constraint, so such that they average out to the prior, then here is the associated value that I get. And I have to optimize this thing over all such beta, gamma, and k, subject to this credibility constraint, which is just, this credibility constraint, which is just like a vector inequality on the a vector inequality that you can see becomes tighter as chi gets smaller. So my sender becomes more constrained in the value they can get as they become less credible. Okay. So now that we have this geometric characterization, we can put it to some use. And so what I actually want to do is show you. So we have in this paper that we look at like forms of comparative statics in the degree of credibility that the sender has. And so I want to show you just a flavor of that in one example. Okay, so here is an example that, I'll just write this. I'll just, talk about it like abstractly in math, but this is the value correspondence associated with an example in which I have two states. Okay, so my states, are either 0 or 1, and say state 1, like I'm writing, the receiver's belief in terms of the probability of state 1, and I have 3 actions, as we had in the simple think tank example, but the payoffs of the sender are different. Okay, so the sender, or I guess what I should say is, the value correspondence is different. So here, the sender likes to convince the receiver that the state is high, and dislikes convincing the receiver that the state is low. Okay, so I have this staircase as my value correspondence. And so let me just talk about, in this example, what's going to happen in sender optimal equilibrium for different levels of chi. All right, so the very first thing is if chi is 1, so if I'm fully credible, then I'm just looking at a Bayesian persuasion problem with this value correspondence, and I haven't drawn the full concavification. It would be this together with interpolating this here, but I have drawn here the form of the sender optimal equilibrium payoff, and a way to implement it is I send 2 messages, and one of these messages leaves you indifferent between the high action and the medium action, and you choose the high. One of them leaves you indifferent between the low action and the medium action, and you choose the medium. And okay, so now what happens if the sender becomes less credible? Okay, so the first thing to notice is that if I were to hold fixed this official report, that's sometimes sending this high message and sometimes sending this low message, and these would have been the beliefs were the sender fully credible, I'm no longer going to have an equilibrium that gives me this value, because if the sender were to, if I were to have such an equilibrium, then the sender, when they have when the 1 minus chi event realizes and they have the opportunity to influence, they would want to send this message. But then the fact that that's happening, irrespective of the state, is going to mean that the actual induced belief when I hear this message is a weighted average of this and the prior. And so I won't find this convincing to choose the high action. But when chi is somewhat high, so in this example, let's say chi is 3/4, I can make the official report more informative in order to buy me some credibility. Okay, so suppose I make the official report such that my low message leaves me at this belief, leaves the receiver at this belief, and my high message would, if the sender knew, so if the receiver knew that the message were coming from an official report, would be convincing that the state is high, then I can have an equilibrium in which the sender pools with this message whenever, whenever they're able to influence, and the induced beliefs are exactly the induced beliefs from the Bayesian persuasion solution. And so I can still have the I can still attain my highest Bayesian persuasion value by just modifying the official report. Okay, now what happens if I make credibility even worse? Okay, so suppose my credibility is now only 2/3. So now a third of the time, my sender is able to influence the report. So it turns out that I can't get my Bayesian persuasion solution anymore. And in fact, for the numbers that I haven't told you with this example, the only way the sender can escape the babbling payoff in this example is to actually give a fully informative experiment, a fully informative official report. But then in the event that I can influence the report, I'm going to send the hi message. And so you're not going to find the hi message fully convincing. And this is going to be the induced sender optimal equilibrium. Now, this is giving a lower payoff to the sender. But one thing that's kind of interesting about this is that whereas before my induced posterior beliefs were, for this example, were like 1/4 and 3/4, now they're 0 and 3/4. So they're actually more spread out. And so this gives us a notion that we show can occur more generally, which we like to think of as productive mistrust. So basically, a less credible sender can actually be providing better information. And the idea is I can be so forced to provide more information through my official report in order to buy myself more credibility, that this can actually provide you more information even when information is becoming garbled by the sender's desire to put their thumb on the scale and influence the report. Okay, so now in this example, what happens if I make credibility slightly lower? So it turns out that if I make credibility slightly lower, then even if I were to give full information, my ability, like basically the influencing sender wanting to send whatever message leads to a strictly higher than babbling payoff, that's going to degrade the quality of information so much that nothing can actually incentivize the receiver to take this high action. And so the sender optimal equilibrium discontinuously drops down to, in this example, the prior level, to the babbling value. All right. So this is something that can happen, that we show happens quite generally in this model, that a slightly lower credibility can lead to a dramatically lower payoff for the sender, dramatically lessened ability to persuade the receiver. Right now, this might lead us to wonder about a robustness question for the Bayesian persuasion model. So we have a big literature full of people asking about what sender optimal information looks like, and it's I think this means it's of interest to understand whether the results for the canonical Bayesian persuasion model are robust to a small degree of imperfect credibility. And in general, they are not. In general, one can, construct examples in which you do not have robustness to a tiny degree of imperfect credibility. Okay, so suppose instead of these 3 actions, I add a 4th action, where the 4th action gives a super high payoff to the sender, but is only incentive compatible for the receiver if he is perfectly convinced that the state is high. Okay, so now the Bayesian persuasion solution will be to fully reveal the state, but if I instead make credibility 1 minus epsilon, then the fact then I can't have an equilibrium in which this super high message is ever taken, because then an influencing sender would want to send such a message, contaminating the associated belief. Now, this example, may sound very knife edge, and that's because it is, and we show that generically, we do have robustness of the Bayesian persuasion solution to a tiny degree of limited credibility. So this, there is a fragility there, but it's non-generic. Okay, so just to sum up on kind of this stochastic commitment model, so we've seen that, the degree of credibility shapes what can be communicated, but that it can have delicate effects. And we've seen that the same tools that worked for understanding the limit cases can also be useful for studying this intermediate case. All right. So now I want to go through in at even more of a high level. I want to go through some other, just rather than this parametric model of limited commitment, thinking about different qualitative notions of what it would mean to not be able to fully commit to communication, and asking, what they mean, and talking a tiny bit about papers that have studied such form of imperfect commitment. Okay, so let me first talk about what we would term manipulable correlation. Okay, so think about, if we think about, go back to the Bayesian persuasion model. So a receiver in this model, they are seeing the message, but they can't observe the algorithm that led to this message, right? They can't, so say I'm interacting with a sender that, in some automated way providing information. I can't see their algorithm. I just see what has been said to me. So we think, cheap talk is arguably like the appropriate model if you're thinking about communicating with a single decision maker who is informed. But in a lot of settings, and in particular in some settings that would be relevant to the EC community, we have an algorithmic provider of information who's sending messages to many different receivers about many different issues, and in a lot of settings, the marginal or some proxy for the marginal distribution over the messages that are sent can be observed. Okay, so you can, I can look up for credit rating agencies what is their distribution of ratings that they give, every couple months I see an article about what Harvard's grade distribution is, and so these things in the distributional sense are more observable, and so this can lead us to a kind of a notion of partial credibility, where I don't worry about commitment to the marginal distribution of messages because that is observable, but I still worry, subject to those constraints, about whether the sender will want to cheat and choose a different algorithm. Okay. So let's say that a disclosure policy, like that a Blackwell experiment, paired with the way the receiver responds to it. So let's say that it's credible if the sender doesn't want to change the joint distribution of states and messages, but I'm going to limit the types of deviations allowed to the sender, and say that they are only allowed to use deviations in which they hold fixed the marginal distribution of messages that they send. Okay, so this is the credibility notion that's proposed in Lin and Liu, which is a beautiful paper that has previously appeared in EC. So first, just kind of an easy case is what if the sender again has state independent preferences. Okay, well in this case, if the sender has state-independent preferences, they don't care about the correlation between the action and the state. They only care about the marginal distribution over actions. And a fortiori, when you hold fixed the receiver's behavior, they only care about the marginal distribution over messages. And so that means that this credibility notion is never going to bind for such a sender. And so if you believe that the sender has transparent motives and you believe that this is an appropriate notion of credibility, of limited commitment, then you're just back to the Bayesian persuasion solution. Okay, now if you go beyond that, Lin and Liu give, I think, the right frame for thinking about this problem analytically. So they notice that really all the sender is doing when we're trying to determine incentive compatibility for the sender is solving an optimal transport problem, right? So they have fixed a fixed marginal over states, namely the prior, a fixed marginal over messages, namely the equilibrium distribution over messages, and they can choose the joint distribution arbitrarily, and they have, once you hold fixed the receiver's payoff, they have a payoff associated with each state message pair, and so they're solving an optimal transport problem, and so from there, we can use, Monge-Kantorovich duality, and characterize their incentive compatibility constraint as a cyclical monotonicity condition. Okay, and so what's required of us is that if you take any finite sequence from the support of the equilibrium, AI theta I, and then let me, for slickness of notation, I'll let A0 be another name for AN. So then what they require is that the cyclic sum of sender payoffs is non-negative. Okay, and so this basically is saying that a particular deviation is not profitable, right? The particular deviation is I have this cycle, and in this state I move a little bit to this message, in this state I move a little bit to this, and this I move a little bit to this, and so on. And I go through the whole cycle, and then I have fixed the marginal distribution of messages, and because all of my deviations are in the closed convex cone generated by these deviations, this is actually sufficient for IC. All right, and so this is useful in the general case, but just to give a flavor, the kind of I think we get some nice qualitative results if we put more structure on the problem, just to give a sense that this credibility notion is really usable. So suppose that the action space and the state space are both ordered, and the sender utility is supermodular. Let me make it strictly supermodular so I don't hurt myself. Okay, no, then the cyclical monotonicity condition is just a monotonicity condition, or said equivalently, I only need to think about 2 cycles. Okay, and this is, up to relabeling, the same reasons, say, that show up in multi-dimensional mechanism design, that I can replace cyclical monotonicity with regular monotonicity. So what is, we can apply this to give, a couple more substantive results. So suppose that the receiver's preferences respect the same modularity. Okay, so the receiver has supermodular preferences, and suppose that it's a model where I'm just trying to convince my receiver, or I shouldn't say it that way, sorry. So my receiver also has this modularity, and I have a binary action setting. Then it's an easy consequence of this result that I'm back to the Bayesian persuasion solution, that my credibility does not bind. And suppose that the receiver has the opposite modularity. So the receiver wants to choose lower actions in higher states. and and I pair that with a kind of a non-degeneracy condition, then as far as outcomes are concerned, I'm forced to get the same outcomes as if I was providing no information, right? So let me tell you about another notion of partial commitment. Okay, so what if I think of my sender as being able to design the game? Okay, so they can design whatever information provision game they want ex ante, but they're constrained by their own incentives in the sense that they're still going to be able to participate in this game, or have to participate in this game as an informed player. Okay, so I can use the revelation principle to say that without loss of generality, I can think about a very specific game and equilibrium selection, where I think of the sender as reporting the state to a disinterested mediator, and the mediator recommends an action to the receiver, and so then my attainable outcomes are given by a very nice polytope in the space of all outcomes, where my constraints are that the sender prefers to report theta rather than reporting some other state when their type is actually theta. The receiver prefers to play A rather than playing some other action when their recommendation, when their recommendation, that should say, is A. And the marginal distribution over states is equal to the prior. And so, this is a nice polytope. You can do like linear programming to like solve for sender optimal equilibrium or other objectives if you want. I want to talk about something different for this class of games, which is recent work that's used the belief-based approach to study it. Okay, so let's think about so we're going to work with the distribution of beliefs and belief contingent choices by the receiver. Okay, so a key observation, if I want to think about an equilibrium through these objects, through the belief distribution of the receiver ex ante and their belief contingent choices, the key observation is that using Bayes' rule, you can infer for any given theta, you can infer the belief distribution conditional on the state being theta. Like you can read it directly off of the ex ante belief distribution. Okay, so two papers that make use of this fact for thinking about communication with limited commitment, or like for thinking about this sort of optimal, sender optimal mediation that I want to raise are, so one, there's this Salamanca paper that makes the observation that, so first, if you were to replace the sender's incentive constraint with the incentive constraints with an associated Lagrangian term, then because the Lagrangian term is linear in beliefs, and adding a linear function commutes with concavification, that means that you can characterize outcomes in this game, like in the mediation game, you can characterize outcomes by concavifying the Lagrangian, being very loose and quick. So now to be able to say more than that for this problem, one very nice paper is by Corral and Dye, which also appeared in EC, and they specialize to the case of state-independent sender preferences. The what they point out, so I'll go back to the sort of outcome distributions that Doron talked about, where I think about distributions over the graph of V. So I'm already building in receiver incentive compatibility. So if I think about Bayes plausible distributions over the graph of V, so all that's left to talk about is sender incentives. What Corral and Dye point out is that you can rewrite the sender incentive constraint as just the property that you have zero covariance between the induced receiver belief and the induced sender payoff. All right. Now, in general, covariance is bilinear. It's not linear. But one thing worth pointing out as just like a little pointer to some tractability is that if you fix the prior, then the zero covariance constraint is a linear constraint. Now, one application of this that they point out is an equivalence result. So they point out that so you could ask, if I have the ability to design the game, or equivalently if I have access to a mediator, when does commitment bind? So or I'll phrase it as, when does commitment not bind? So when is it the case that I can actually replicate my Bayesian persuasion value as an equilibrium with this mediator? And they show that I can only do this if I could do it without the mediator. And intuitively, if you think about the Bayesian persuasion problem, we know that you can think about solutions to the Bayesian persuasion problem by taking a tangent hyperplane to V hat. And we know that Bayesian persuasion solutions are just going to V hat at the prior. And we know that Bayesian persuasion solutions are just going to correspond to Bayes plausible belief distributions that live in this hyperplane. But once I'm looking at distributions that live inside this hyperplane, the only way I can have zero covariance between the level and the location is if the hyperplane is flat, or at least flat on the dimensions I'm using, which corresponds to equalizing payoffs across my messages. Okay, so I have mismanaged time, and let me just say, okay, so I'll be very I will be very brief on this one and just say, so mediated communication does require it requires some commitment power, right? So I need something like, I need the ability to design the game, or I need a trusted third party, or at least I need some sort of ability to commit to randomization. And so you can ask what you can do without even this much commitment, sort of like in a fully decentralized way. And a natural model of that is that of unrestricted, repeated bilateral communication before the decision is made. And this buys you something, because if the sender and receiver are both talking, then together, or even just the receiver's messages can serve as some kind of randomization, and that randomization can help smooth out incentive constraints for the sender. So Aumann and Hart 2003 give a geometric approach to understanding the attainable outcomes. They give a correspondence that like they name it from the primitives of the problem, that takes in a receiver belief and spits out a sender payoff vector, such that they show that the following are equivalent. So such that they give, I'm just trying to decide whether, sorry. So basically they characterize whether a payoff vector is attainable, payoff vector for the sender is attainable in an equilibrium of this long cheap talk game, their characterization in terms of the correspondence is that let me phrase it as, it is an equilibrium payoff vector if and only if I have a bi-martingale, which is a fancy term for a martingale where I'm either only splitting in beliefs or only splitting in payoffs at any given time, such that this bi-martingale starts at this payoff vector paired with the prior and ends in the graph of this correspondence. And a prior paper by Ullman and Hart shows that, you know, this can be equivalently characterized without, you know, referring to these stochastic processes by just talking about separating points from the graph of this correspondence by biconvex functions. Roughly, this is the analog of the appropriate analog of a point is outside a convex hull if and only if it can be separated from it by an affine function. But for these for characterizing the biconvex hull. Okay, I think I've now just gone completely out or over time. And so I would just say this was all even within the realm of imperfect communication models in which the belief-based approach is relevant. Even within this realm, what I've given is a very incomplete overview of a few things. But, you know, I think this is a super fun literature in which these tools are actually quite useful. And so yeah, I think it's a fun literature that you should all read up on. But okay, thank you so much for your time.